Okay. Good afternoon, everyone. I feel like there are lesser people in the first day than the number of people who registered, but that's okay. So this is deep learning and modern applications. So if you're not signed up with 576, which is IDS 576, then this is probably the time to find your class. So this is deep learning. So I hope everybody's interested in deep learning these days with all the things that you can do with many of the vendors, ChatGPT or Cloud.A or Bird and so on. So I'll go through the syllabus document. Is actually, I hope everybody has access to Blackboard. If not, let me know. Let me know sometime during the break or after the class. But much of the course material that we're going to cover today is at least on GitHub itself, so you can actually follow along pretty much. So what I'm going to do for the first few minutes, maybe 10 minutes or so, is just give you a structure of the course so that you can, again, decide whether this is the course for you or too easy or too difficult. You kind of want to figure that out. And also, what is your expectation from the course and does it match what we teach you. And then we'll get into the course itself. So today's lecture is actually pretty lightweight. We're just going to review some machine learning concepts, basic machine learning concepts, in the sense that in supervised learning, if you want to do classification, then what are some of the ingredients that you will kind of play with. And then one idea, which actually will not spend too much time on in the course, but it's a key idea that kind of enables much of the ML training these days, which is gradient descent. Okay, gradient descent is a specific technique. Those of you who've done 575 might have played with gradient descent in many of the regression type problems. So we'll look at one concept called backpropagation, or basically it's just chain rule in calculus. So we'll just revisit that. Okay, so that's the new thing. Before that, it's going to be just a review of classification. And and if you have questions and points to make, you can make them anytime during the lecture. And I see some people who took some other course with me before. That's good. Okay, so in terms of the structure, I hope everybody has seen this page before, or if not, have a look at it. Basically, this course is about, if you want, my version of the, what this course is about is actually, it's a very basic introduction to deep learning. Okay. Now, when I say very basic, I'm just comparing it to what's available out there in terms of course material, or even the types of tools you can play with, right? If you just go to pytorch.org and then go to tutorials, the types of tutorials that you see is going to be advanced than what we'll see in this course. But what's the advantage of then taking this course is just if you're, somewhat lazy like me, then this is a good, way to kind of spend some time on each of the basic concepts. It can parallel other things that you kind of, if you are really interested in deep learning, you can just go to this course, which is going to be somewhat of a safe zone, and then try out the more harder things that you come across online on GitHub or through other channels, right? So that's what this course is about. So it's really a basic introduction to deep learning. It says modern application. So that part basically means that much of the time you tend to work with tabular data. So here we'll try to, obviously tabular data can also be used in some of the models that we'll discuss in this course, but we'll try to kind of spend a little bit more time on text and images. Okay, text, you've seen text applications. If you've not played with ChatGPT, you should sign up. But so text and images are basically, again, at the end of the day, they're going to be numbers, just like tabular data. But there's some, some transformations that are done. And so we'll discuss them as well. Okay, so that's going to be the emphasis a little bit on the data side. Okay, so if this is what you want to, if you want to get into NLP, natural language processing, there are courses in the department which, short courses, 2 credit courses which focus on NLP. But in this course also we look at NLP. Okay, but although our scope is not just natural language, but also images, tabular data, and also decision making. Okay, so which is most of these forecasting models or prediction models that we'll see are going to be, you can use them as just just to make predictions, but at the end of the day you also want to automate decisions. Okay, you just don't want to automate predictions. And so there is various combinations floating around in the literature or in the area of how to combine them. You can do just a 2-step process. First, just focus on predictions, get good predictions, and then somebody else downstream, some operations research person and a revenue management person or somebody else we'll take those forecasts and then do something, okay, with it. But there are ways to also combine them, combine both decision making and learning. And why do you want to do that? Because sometimes you don't have, at the beginning of time, you may not have enough data to make good predictions. And so then you make some predictions. Actually, the predictions lead to some actions in the real world. Then you get feedback, and that feedback becomes an additional training data on which you again train and again make predictions. And those predictions are fed into actions. Actions get feedback, and so there's a a loop that you can enable if you kind of understand decision making as well. Okay, and so that's the last part. Anyway, I will revisit them in the slides that we have for today, but that's the objective. So I hope I covered the key ideas in this course. So if you're already an expert in deep learning, this is not, this course is going to be a basic review for you, which is fine. You can take it, and it's good to review in a classroom setting. So there is a topics, a lot of acronyms. We will go through the acronyms in their specific chapters or lectures. And so this tentative list is just a summary, but there's actually a detailed information right below. So before that, logistics. This is a location. It's a 2.5-hour meeting time. Hopefully, I'm not the only person speaking throughout. We'll take a break about an hour and 15 minutes into the lecture, a short break. Office hours, same day, just before the lecture session. You can also meet, obviously, through email on separate occasions if that slot doesn't work for you. So we have the course structure, and this is where I want to give one more key aspect of this course, is that it's very project heavy. Okay, so the content of this course, obviously, we'll go through some architectures and some ideas about deep learning, key ideas on deep learning, but really, as you can see, the first within the first half of the course, we finish the key assignments in this course. Okay, and really the second half is really about spending time on the thing that you want to do. Okay, some of you are here for potentially, you want to do something and you want to use deep learning for what you want to do. This is a good time to kind of do that. Maybe you want to add that as your project in your CV/portfolio, or it's a project that you want to do for your research, whatever. So that's something that you really should align with this timeline, because you don't want to do double work, right? I mean, so this is so you can see the second half is really about projects, and so this is a tentative idea of like how we're going to progress. Maybe a lecture session will be turned into a project, discussion session perhaps, and so on. But we just have three assignments, okay? And those are the deadlines. So in 2 weeks there's an assignment, one deadline, and so we'll see what the assignment is and what the content is soon. Okay. Yeah. So don't miss any lecture or any session here. Okay. So if you're gonna schedule your interviews or visit somewhere else and so on, definitely try not to do that. Yeah. Topics. There are actually listed. There are only 12 topics. There are a few more that we can add depending on how we cover. Okay, we can be slow, we can be fast, and we can pick and choose. But this is a tentative list of how we're going to progress. Okay. Textbooks. Here are some recommended ones, but you don't have to. I mean, unless these are actually useful for people who are also doing advanced study in this area. So it's not only for beginners. So if you don't want to look at these texts, there are other texts, or maybe like the third one, for example, is a little bit more introductory, as in it's not heavy in terms of theory. So you can look at any of these texts, but it's not necessary for this course. There's a collection of resources or reading links that are available per lecture. That's actually here. So the lecture goals, first lecture, there's not much links, first couple of lectures, but you can see that there are going to be some links that you can rely on to kind of understand some additional context about these lectures. Okay, so some formatting issue, but there are links here, and they may be populated. There'll be more links later on. Okay. We come back. Okay. So here's the big question, right? You want to do deep learning, but where are the resources? Unfortunately, we don't have resources from the UIC side. What do I mean by resources, right? Like you would like to have a GPU available, just because you can really speed up computation. You can actually see almost a 10x less time, even more actually. But let me just give you a ballpark number. You can actually do what takes 10 minutes within a minute. Okay, so that kind of is kind of useful, but we don't have that hardware separate, so we will rely on free resources. So Google Cloud is one, but there are others. Kaggle notebooks, I think, and a few more. You can reach out to me, or you can talk to your friends in the class. So try to rely on those resources, and they do have, I guess, GPU or some accelerated computing hardware behind the scenes that can speed up your training and stuff. Okay. The language is Python. In fact, we're going to do very, I would say, beginner level Python, in the sense that we're not going to be strict with respect to, type hints or any of the modern features that you see in, Python 3.9, 10, whatever, 11. We're going to do something simple, but that doesn't mean, that's just to keep the focus on the content, not. But if you want to write really good code, you can also try to aim for that. And mostly, as you can see, I'm just using a Jupyter notebook to discuss this, but these are the kind of tools we'll use. So software-wise, Python, and then obviously many packages in there. Not just these, there are many packages now that we can use. But for assignments, it'll be you have to kind of write those. You don't want to import somebody else's package and just say package.execute and then get the solution. Okay, that's not a solution. Okay, so to keep the logic simple, I'm suggesting that you have strictly 3 students to group together for the assignments. Okay, so I'm trying to make it a little bit more lightweight. So if you really want to keep it challenging, you can go solo and do these assignments if you want. And also if you want to do the project, but I think that's quite challenging. Okay, so my recommendation is you group up in teams of 3 and work on the assignments and the project. Okay. Okay, so this is actually, I need to spend some time on. The project is actually, as I said, is an important component of this course. What is a deep learning project? What is something that we can do with the limited resources that I just mentioned? There's some discussion in the project page that I will not go through in detail right now, but something that you can look into. For example, I can just give you some context. Last semester, the theme was all about object detection. Okay, object detection is a problem where you have a stream of video, like some webcam or some security camera or something, and object detection is all about. It not be a video. It could be even an image. It's all about tagging objects in that image. Okay, tagging objects means putting a bounding box, a square or rectangle around objects of interest, and saying what class it is. Okay, so it's like a kind of a classification problem, but also a regression problem, because you need to put bounding boxes, so which means some coordinates in some space. So last time the theme was about object detection, so everybody was doing some aspect of object detection. Okay, that was something we tried out last semester. But before that, for example, anybody could do quite a different set of projects. Okay, so somebody was trying out language models, somebody was trying out time series forecasting for finance. There was a very wide variety of things. So projects can vary like this. Just give you a sense of what projects could be. But we'll kind of final down on what the theme will be. So I have 2 options right now. One is to make the theme like LLM specific, or just keep it general. So I'll kind of let you guys know soon. But if you already have some project idea, as I said, especially some of the PhD students or masters who are doing research, you should talk to me, and as long as it fits within the theme of this course, you can do both, right? Yeah. So please do note that late submissions have an automatic penalty, not just for the project, actually, even for assignments. So just think of the deadline as a few hours before. Okay, so if you try to submit exactly on L01, it's unfair to somebody who kind of met the deadline. Okay, so yeah. So again, to re-emphasize, the project is 60% of the grade. Okay, so really the lecture content is more about, as long as you're interested, let's discuss different models, different aspects of deep learning. But that doesn't really count too much, right? It's course participation is 10%, just to see, like, yeah, I'm understanding, what's being discussed and so on. We currently don't have a TA assigned, so it's just me, but that's the course participation aspect. Project, as I said, has a couple of milestones. Intermediate milestone just means you have a proposal for what the project would be, and maybe you've done some preliminary analysis on the data or the models or some literature survey on what types of models you want to work on. And the final submission is actually what you try to do, hopefully something interesting, and then you kind of document it. Okay. Assignments, 30% of the day. These are assignments just kind of reflect what is being taught. So what we'll see today will be part of assignment 1, as like one question perhaps. Okay. But the assignments are already out there if you want to look at the assignments and on the Git repo. Try to do it. Try not to copy from other places. And finally, some information. This is just standard information that you probably have seen in other courses. So if you need any additional accommodations or any constraints that you have or anything else, okay, so you should talk to the instructor or other resources at UIC and in the department. Okay. Okay, now I finished this walkthrough of this the syllabus. So any questions about this? Okay. How many of you already trained a neural network before? Just one?
What is the question?
How many of you have already trained a neural network before? Okay, 3. How many of you have used a neural network in the sense like, import transformers, let's say, or import ChatGPT and put the key and then try it out? Okay, a few of you have tried using models. Yeah. So using models, I guess, is the easiest step, and then training models is, I guess, a little bit harder than that. So it looks like a good chunk of you have already tried something to do with neural networks. Okay, and we'll see actually the connection to, for example, logistic regression. Logistic regression is actually a neural network as well, without some layers in there. So good. So perhaps I'm just guessing that maybe the course material is a little bit easier. If so, I can speed up. Let me know. Okay, so if there are no questions, then we can get into the lecture part of the course for today. Okay. It's as I said, you can always interrupt, and if you have something to add relevant to the discussion, you can ask questions. Certainly, if you have a question, I think that means somebody else probably also has a question. So so that's the rules. You don't have to wait till the end and only ask me separately after the class. Okay, you can always ask a question. Okay, so so this slide I got from the same repository. So if you just you can either git clone the repository, or you can just download it from the web page and unzip it, and then you can go to the slides directory, and that's where you'll find this. Okay. So today's outline was this. So actually, today is not a very heavyweight lecture. So it's a review to see how you can ease into, get a little bit more feel for what the course is about and ease into the course. Okay. But next lecture onwards, we're going to start looking at some canonical example models in this category. So, okay, so we're gonna again redo the introduction to the course, but now through some examples and motivated, basically introduction to the course, just more motivation about some examples that have kind of made the field interesting. And then we will review classification as an example. We can also do regression, but let's do classification. And we'll look at chain rule or backpropagation, which is the kind of workhorse behind training anything these days. And then we look at I think feed-forward neural networks we'll look at next time, perhaps. But we'll see why would we need feed-forward networks. Okay. Okay. So as I said, there are going to be several different tools. I call them tools because at the end of the day, you want to achieve something. You want to predict better. You want to understand some data better, or understand, take decisions. For that, you're going to use different tools, right? Prediction tools, and some of you, and probably a good chunk of you, have done some basic course in machine learning, so you've probably seen several tools. Okay, k nearest neighbors, linear regression models, or logic regression / other things, XGBoost as a specific implementation of boosting type of models. So there are many models under the machine learning, I guess, toolkit, under which we're going to look at specific tools related to these two broad, I guess, categories. deep learning and online/reinforcement learning. The second one is actually the one which is going to be a flavor of decision making. Okay, so I remember at the beginning I said the course has certain key points, and one of the key points was we're going to talk about decisions as well, and not just focus on prediction. So the second category of things, one flavor of decision making is called online and reinforcement learning. Okay, so let me start with a disclaimer first, and then we'll get into the course. So what is the utility of the course? Just because you do go through this course, or go through deep learning content elsewhere, perhaps doesn't mean you can solve everything. You do need to have, and we are in the business school, so we do need to have like an approach where we understand what is the business goal, or what is the endeavor of the project. Doesn't have to be in a business setting. What is that you want to solve, and then backtrack into what broad categories of capabilities you need. It could be product, it could be just service, as in people that can solve achieve the business goal. And then depending on the category of capabilities you need, which involve, for example, how are you going to deliver your solution? What is the data that you're going to use to catch, build or solve or get a solution. And then one of the steps, or one of the items in that list is going to be techniques. Okay? In the techniques world, there are many techniques, as I just said. You've done several courses in terms of techniques, and one of the techniques category is deep learning. Okay, so it really, how much can deep learning help you? It has to kind of have a good, strong connection to the overall value that you're creating. Okay? If you're not, then you could be building all sorts of models, but they may not be helpful. Okay, and many times it actually happens that you build a really good model, but it's not actually solving the business problem. Okay, when I say really good models, you may have good cross validation losses, or good in sample performance, good loss values, but doesn't translate to value creation. Okay, so this is a very important thing to have that perspective. In not just for this deep learning context, but in terms of any technical solutions that you're seeing in this course. And with that disclaimer, so I call it a business analyst toolkit, but it's just a toolkit for data science, right? So I mean, I'm actually not listed many of things that you have also done, but let's say if you focus on prediction and exploration, I just put 2, but there are actually many other exploration techniques. Exploration just means that I'm not building prediction. I'm just building a prediction model. I'm just trying to understand my data, like segmentation, slicing and dicing, and stuff like that. On prediction side, there are many tools. Here are a few names that some of you may remember from your previous courses. And the 2 things that we'll add to this list is going to be neural networks and online and reinforcement learning. Okay. Now, why does online and reinforcement learning come under prediction? Is because it's not just about decision making. That flavor of decision making involves understanding the prediction part as well, and that's why I've just categorized it here. Okay, so those things in purple are the only new things that we're going to study in this course. Okay, so it's a little bit of a letdown. We're not going to conquer the world. We're just going to do a little bit, some more tools in our toolkit. Okay, in terms of data, the types of data that we'll look at in this course, we'll look at mostly unstructured data, or at least we'll talk more about unstructured data. And I'm calling it unstructured, but actually, it has structure in it, obviously. So structured data, I just mean something that is already tabular, or at least where you're making measurements at different timestamps or in some order, and so you have numbers, represented in a nice way, like a matrix or a tensor and so on. Okay. And obviously, even structured data will have a lot of variations. It could be all sorts of fields. Doesn't have to be just these. Just doesn't have to be integer or ordinal or binary or categorical. There could also be textual data also at a given timestamp is also structured somewhat, as long as you know how to transform it into numbers again at some point. Okay, and unstructured data from the get-go is going to be things like images, videos, text, and documents. Okay, so here you could actually have both types of data at the same time, and so if you have seen the word multimodal, it can apply to this where you have multiple types of data. So multimodal could mean I have both images and text, or multimodal could mean I have both images and numerical tabular data. Okay, so There's a lot of variety, but we'll kind of talk about this more because it turns out, at least deep learning, certainly the techniques, the models are applicable for any type of data. But it's there's a little bit of a nice advantage you get if you work with unstructured data and deep learning is because it kind of reduces what is called feature engineering effort, right? So with tabular data, also you can ignore feature engineering and just say I'll throw everything, all features into a model and just see what works. But especially if you have domain knowledge, feature engineering can really give you a good bang per buck in when you have structured data. And it's actually what most, like for example, think of domain like finance. Okay, people want to understand what they're building, and also that means that they want to spend time on feature engineering and interpreting transform variables and so on. Okay, so there, which feature engineering is actually valuable and useful. In deep learning, we try to avoid feature engineering by just kind of picking the right model, which kind of is the right complement to the type of data set. So, for example, for images, in the next lecture, we'll see something called a convolutional neural network. And so, just because the definition of that model, it takes advantage of, oh, it's an image, and so you don't have to explicitly do feature engineering. Okay, we'll see that nice complement effect later. Okay, so that's about deep learning being only a few line items in the toolkit and the type of data that we'll look at in this course. And the last point is about decisions. There are many types of decisions here. I just wrote a couple of examples, which articles to show recommendations, for example, how to price products for example, if you do revenue management, things like that. And most of these things use prediction. Okay, we want to predict, hey, if I showed X, then would the user who came to my website read it? Or if I take Y action, would the spread of COVID decrease, right? So there are many decisions which need forecasts. But there are situations where you need to take decisions repeatedly again and again and again, right? So sometimes the decisions have long-term goals where your decision impacts the state of the world in the future, and so you should be careful about making a decision, not just the immediate revenue. For example, let's say you price your products too low and you get a loss. Hopefully you build loyalty so that next time, even if you price high, people come. So there's some long-term aspects to decisions as well. Okay, so online and reinforcement learning is an area, is a specific flavor of decision making, which takes this learning on the go problem, in the sense that there is a long-term aspect to decisions I'm taking, and I can take decisions and also get feedback about how did I do. For example, if I'm doing pricing, I can price low and see, the demand increase like a lot, and I price higher, maybe I see demand lower, and so I can learn what is the actual demand curve and maybe maximize the profit. So and maybe if you price lower, there's a longer term effect of people becoming more loyal because they use your product and so on. So I'm just telling everything in English, but later on, towards the third part of this course, again, towards the end of the course, we'll actually really formalize it. Okay, and it will be an interesting mix of understanding decision making and then tying it back to all the deep learning models that we've seen, and we will see in the first few lectures. Okay. So for now, it may seem like, what is this? But later on, we'll connect it back to deep learning as well. I think this I've already just discussed it. Basically, the themes are, in addition to obviously deep learning tools that we study, variety of data and decisions into the mix. Okay, that's two extra things. Okay, I think I'm just saying the same thing here. So let me come back to some examples. Okay, so this is just going to be 3 examples for the 3 things, 2 or 3 things that I mentioned. Firstly, just an example for deep learning. This is about 11 years ago that a big delta happened in machine learning or prediction space, which is kind of ancient history for if in deep learning, but still it's worth knowing. So about 11 years ago, actually 2012 or maybe 2011, 2012 was the year when there was a model that was proposed, or not proposed, but actually trained and actually worked well. It's called AlexNet, and we'll look at it later. Okay, AlexNet, because the name of the author is Alex from Toronto, probably. So what is this? What is this slide trying to show? So there's an image classification problem There was some researchers few years before had set this problem. Okay, hey, here's a bunch of images, and here are the classes of those images, and build as good of a model as possible that can classify those images. Okay, it's just a plain vanilla classification problem that you already know. Like for MNIST, you guys must have done like a 10 class classification, for example, using even logistic regression, for example. So different teams are allowed to compete, different research teams and companies and so on. And so this is showing the error as a function of years, okay, top performer in each year. And in 2012, there was a huge jump from 26% error to 16% error in absolute terms. Okay, it's not related. So it's like 10 points less error in absolute terms. And this is actually, you may say, okay, 0.26 to 0.16 seems like a very small difference, but it's a big, jump. Okay. So this was enabled by a neural network architecture. Okay? So before this, actually in 2011 and 2010 and so on, much of the effort in terms of winning solutions were actually SVMs at the top, support vector machines that everybody knows, and then a lot of feature engineering to get to the right features, and then doing multi-class SVM, which basically is one versus all versus all variations that you have heard of in the previous classes. Okay, so this was the big shift in 2012, and then obviously in the future, since then, a lot of neural network-based architectures have done really well, and now the combination is kind of useless because if you already are reaching at this level of error or whatever 93% accuracy, you're kind of similar to humans who actually annotated the data. So if you do better than that, what does it mean, right? Are you like we don't know what does it mean, right? So this saturated, and so now people still, I think, compete. But yeah, that's the image net large scale visual recognition challenge. That's the huge acronym here. It's a large problem. Even today, actually, we can't probably do this on our laptops and so on, because even this subtask, the original data set actually has 22,000 classes and 14 million images. Okay, that's a lot of data. So if you use Google Photos, iCloud, or some I don't know how many images you guys will have, but it's a lot of data, right? So even the smaller, this particular task, which this figure corresponds to, is only 1,000 classes, okay, and only 1.5 million images. So it's even hard to do it now with, let's say, scikit-learn or something easy. I mean, it's not super easy. What I'm trying to say, it's not like MNIST yet, but obviously, in terms of research, in terms of capabilities of humanity, obviously this is a solved problem now. So that's one of the reasons why we should study deep learning. Since then, neural network-based architectures have not just been doing image classification, but many different things. And just to give you some historical context, we'll not talk so much about history throughout the course, but neural networks are not new. Neural nets and deep learning kind of synonyms. The deep part we'll study later, but they're not new from a long time ago, right? And it was applied to digit recognition back in 1998, which is essentially MNIST type data, with actually success. Okay, so the author actually got the top prize in computer science for this a few years ago for doing this work, in addition to a couple of other prominent researchers. So what changed, right? So from about a decade ago or 15 years ago, what changed is the access to compute. Okay, so we had access to computation. So if you remember all the, especially the PhD students, if you look at research papers pre-1990, they won't have too much data. They'll have like 100 observations, and then they'll try to infer something, right? So in the 90s, compute became, even before, but let's say 90s, compute was super mainstream. So everybody had access to computers, 90s and let's say early 2000s. That was CPUs, right? So now in GPUs, which were actually originally designed for rendering and 3D applications and then gaming, now became useful for doing machine learning. Okay, and why? Because behind the scenes, both gaming and rendering and physics, all that stuff, they work with tensors, and so we will also work with tensors, or basically matrices, and so the same hardware can be used to really compute fast on them. and access to data as well. Okay, so hard disk sizes, 20 years ago, 1 terabyte was amazing. Today, 1 terabyte is like, okay, very normal, right? So that's what changed, and that was only 10 years ago when you guys were in high school, perhaps. Now there's a lot of caveats. I think I threw this even at the beginning, like 3 slides ago, which is that achieve great performance in some tasks. I mean, I would say this is not true anymore, second bullet point, but there's still a lot of scope for improvement. Okay, so as you can see, even with, for example, the most state-of-the-art deep learning models, which are kind of back ChatGPT and variations, Llama and so on, they have a lot of scope for improvement, right? So they are, sometimes producing very confidently wrong answers that you see. So there's a lot of things, and there are, I think, in terms of impact, in terms of societal value, there have been multiple billion-dollar companies that have been created on just some very specific aspects of these things. So there's a lot of scope. It's not a solved problem. It does achieve great performance in some tasks, but there seems to be still a gap to fill. Okay. There's always this risk of, are they trying to replace humans? That's a fine balance, right? So there are some tasks where if it's where deep learning could replace humans, but in some places they're extremely bad, so you should not be doing that. So we will not get into that detail, but the caveat is it's not a hammer that kind of replaces your linear regression or random forest and stuff like that. Okay, so actually linear regression is really, really good because you can interpret a lot of things and you can really understand what's going in and what's coming out. Okay, although we'll talk about interpreting deep learning models also. Now let me just shift to so deep learning. I'm not going to give more examples. Obviously LLMs are there. I didn't want to open OpenAI's webpage. Let me get into the next the second part of the course, which is also interesting, is about mixing learning. When I say learning, I'm talking about prediction, mixing predictions with decisions, right? So here's the page for, so this is actually, again, from some research work but by some authors. This is just a page for a website, right? MSN.com. It's a Microsoft web property. So what's the decisions that they need to make? They, as in the platform, in this case MSN, has to make decisions when users visit users visit the website. Okay. So what they do, and much of it will not make too much sense right now, is that when users come, typically they may have a Microsoft account or something like that. They will have some information that they will reveal, right? User demographics, some feature vector, history, that they will reveal. And then maybe the editorial team at MSN will create, okay, these are the articles that are interesting for this today based on latest news and so on. Okay. All that goes into some box, which is like a prediction model, but with some extra bells and whistles. And that generates a list of things to actually put on the website based on that user. So it's not a fixed static website. Okay, it's not static. Depends on the users. Depending on the user, maybe the user is interested in music, then there'll be music articles, and if the user is interested in sports, there'll be sports articles. There'll be a ranked list. But the interesting thing is this is not a model that's trained once a month and it's in some sense static. Okay? It's not static. Based on users' responses to that, whatever it produced, it made some decision of what to show. User responded by, hey, it's interesting, it's not interesting, or some variation like that, or how long they studied, read the article and so on. Based on that, there is some logging of that feedback, and the feedback goes back into improving that green box. Okay, the green box is essentially a prediction model, but it's you can say it's as if we have a for loop for retraining again and again and again with extra data, but that itself is not enough, and that's why we are studying that topic. If it was just as simple as just retraining again and again and again with new data, that would be just like 2 minutes, a small comment. But you need to do a little bit more because of some issues that arise in this type of feedback loops. Okay. Another example of the same nature, actually, although on the surface it doesn't show like that, is this. Okay, this is again pretty old example now. Actually, there is AlphaFold, for example, could also be in this category. This is a image from, I guess, a magazine called Nature, a technical magazine called Nature. So where this was kind of set up when a team of, I guess, Google DeepMind on the left defeated the then world #1 ranked player in a game called Go. Go is like a board game. It's like chess, but much, but it has its own stage space and all rules, and much more complex actually in terms of at least computers to solve. Till then, actually, no software was able to compete with top players in the sport. But that was a historic moment, and now just like chess, computers can do way better than us humans. So that is actually based on the idea of, again, at least to get to a software that can actually compete with human, behind the scenes, how do you build a software involves the feedback loop, because it has to try something, make some decisions based on its predictions of whether it's a good move or not, and then it'll get feedback from the opponent that, hey, I just took your territory, or whatever is the language used there, and so it learns from that feedback loop. Okay, so that feedback, I guess that's why we have the word reinforcement there. We borrowed it from, I guess, that branch of study. So that's why this is also a decision making setting, okay, with some predictions built in, and we'll see that case study towards the end of the course. This is just a snapshot of Atari games. So I don't know how many of you played these 2D games. These days, I guess everybody probably plays 3D games from the get-go, but these are just a snapshot, screenshots of different games. Okay, think of like a mobile game where again, long time ago, I guess now 10 years ago, researchers showed that you can just use the same architecture, deep learning architecture, and what's called a reinforcement learning algorithm to same architecture, almost everything same. As long as you can play with each of these games by itself, it can learn, and actually really compete, or not even compete. This is just a software playing with a game. The software can get scores which are much higher than humans. Okay, so this is 10 plus years ago, and now actually we are way better. We, as in some people, are way better at doing this. But we'll have to get there to understand what are the moving parts. Actually, we can. Some of you and some students have done projects like this before in the class. Okay, so again, I just want to wrap up this really introduction / motivation to the course. What I covered is basically saying that we don't solve everything. It's not a hammer that replaces everything. It just adds more things to your toolkit, and there are interesting flavors that we'll study in this course, which may set it, which hopefully complements some of the online material that you'll see, like for example on PyTorch or Kaggle or elsewhere, or Coursera or YouTube, wherever. The caveat, let me just repeat the caveat once more, is that really when you go into projects, and I know many of you do other courses, and so including maybe capstone projects and stuff. At the end of the day, the businesses really care about what actually moves the needle in terms of their short-term and long-term goals. Okay, businesses do have long-term goals. Maybe they have a mission statement, and they also have short-term goals, maybe quarterly or maybe next year they need to release something or improve something. So at the end of the day, whether prediction models themselves, but not specific to deep learning or some other technology, how much is it timely, and does it really improve something towards those long and short-term goals? Okay, that's the most important thing. Everything behind, it could be even a linear regression model, doesn't have to be a deep learning model, as long as it provides value. Okay? So it should not be wedded to the solutions, be wedded to the important problems, identify the important problems in the context, in the project settings. Okay, so any questions in that, walk we did through some examples? Okay, now we'll be very concrete. Okay, we'll be slow, concrete, but we'll do a review of classification and then introduce backpropagation. Okay, so no questions. Is it because it's a hot day, or is it you're getting ready for the actual meet? Okay, so let's actually do a warm-up, which we'll look at classification. It's just a recap of classification. is not a complete recap because we'll skip a huge chunk. I'll tell you beforehand. We'll look at only what's data, what's a model, what's the loss function, and what's optimization. Okay. Yeah, these are the 4 things that I wrote down when I created the slides. But there's one key thing that I missed from this, which is the whole idea of diagnostics. Okay, model diagnostics. Obviously, if you're doing linear regression, you'll get model diagnostics sometimes for free to some of the packages, stats models or something like that, where it will say, hey, p-values, and you'll get some interpretation of how well your model fitted to the data and so on. I missed that important bullet here, but just remember that is actually important, very, very important category actually. But with that caveat, these are the 4. I think these are the 4 ingredients that go into like pretty much describing what a classification setting is and solving it. Okay. Do you have any points to add here? Right. How many of you have not done 572 or 575? At least the one IDEA students. Everybody has done 572 and 575. You're doing 575 now, Professor Montelli. Yeah. Okay, great. So I mean, you'll see some of these and on backpropagation as well in that course. But okay. So, but this is a recap for those who've done 572, because in 572, in addition to data mining, focus, you have built prediction models. So, what is the objective of classification, right? So, what does the end user really want to do? I want to get some new data point that I want to classify as X or Y or Z. Okay, that's what the end user wants to do. You, as a solution provider, will have to actually gather some data, compress the data into a model that can do that task for your end user, right? So, so as a designer, you need a few things, right? So, but what the end user wants is just this. Just example, a classifier that performs really well, as in hopefully doesn't make bad classifications. Now, to design a classifier, at least at the first order, you need these things: a set of training data, model specification, like which class of models are appropriate, especially if you want interpretability and something about the domain, about the domain that you're working with. You want to specify which types of models you want to use. You want to define what is your loss function, because we have seen many variations of loss functions, perhaps mean squared loss and mean absolute deviation, and maybe some other losses. We'll see some losses later. So specifying the loss function is actually also important, because maybe you care about what you care about when you specify the loss function. You care about how you're gonna penalize the classifier, you as the designer of the solution, but that may deviate from the end user's way of thinking of when the classifier makes a wrong classification. Okay, so there could be some gap between what the end user thinks in terms of errors versus what you think of errors. For example, let's say your classification loss is, let's say, binary classification loss, or sorry, let's say it's a 0-1 loss. Okay? It's just either you are correct or you're off. Okay? But the end user, perhaps, as long as you classify, let's say it's the cat image, as long as you classify as a dog and not as a chair, it's still okay, perhaps. That doesn't make sense for that's not exactly compatible with what you thought was the loss. Okay? That's just a simple example of showing that there could be a gap between what you specify and what the end user really cares about. Okay, and finally, if you have these things, how do you actually get to the best model? I said, okay, you already specified the model class. Okay, I want to search a prediction function or a classification function in the class of linear functions. Okay, that's the specification number 2. But how do you get to the best linear function? Okay, that requires some work by basically some computation. Okay, and that computation, that optimization, much of machine learning kind of uses continuous optimization, and therefore uses gradient-based techniques. Okay, so we'll see that's why we're seeing backpropagation later.
Optimization is basically when we create a model, we change the variable like here and there, find the best performance. Like is that?
Yes, when you do it, then even though you're doing trial and error, yes. So a lot of things are about optimization, right? Whenever you're tuning things to get to a good place, as in good answer or so on, you can always call it optimization. But here I'm meaning something very specific, and we'll see that in a couple of slides. Okay, optimization is all about tuning to get to the best solution, and best also needs to be defined, but we'll define it. Best is actually defined by the previous bullet point, which is actually. Yeah, but let's see. Actually, let's go through these four aspects again. Let's pick a domain, right? Like vision. Vision just means images and video and so on. Okay. So first of all, I mean, if you have never worked with vision data, like then you're saying, okay, what is an image, right? You want to kind of get a sense of what is an image, or it could also be a video. But let's start with an image. It's essentially a bunch of numbers, right? So once you already have an image on your, like in a folder on your hard disk or whatever, right? It's already a bunch of numbers. In fact, if you can actually read it using any software, like we can read it in Python, right? Using different libraries, and you'll see that actually it's not always the case. But here I'm just giving you some examples. So sometimes it's a bunch of numbers, but each number varies between a predefined range. Maybe it's an integer between 0 to 255. Okay, but it doesn't have to be like that. It could be a number between 0 to 1. It could be a number between -1 to 1. Anything. Typically, it's a three-dimensional array. Now let's parse it a little bit. Three-dimensional. Why three? Is because it doesn't have to be always the case, but typically images have three colors, three colors which compose that image. Okay, there's a red channel, a green channel, and blue channel. RGB, I guess, is the acronym there. So, so an image essentially is basically three matrices. Okay, three matrices. What are matrices? A bunch of, I guess, boxes with cells, and you have numbers there. And each matrix corresponds to intensity of the channel. Okay, how intense is the red color in the image is captured in the red matrix, and similarly how intense is the blue color in that image is captured in the blue matrix, and so on. You kind of put them together, and that is a three-dimensional array or a tensor. Okay, that's what an image is, and we can load an image. I'm not going to do that right now in Google Colab, but it's easy to load an image and see how it is. Actually, we can see it towards the end. Okay. So what is an image? It's a bunch of numbers put in a certain way. Okay. In particular, it's a three-dimensional array. If you don't want to think of a color image, then think of a black and white image like MNIST data that you have probably some of you have worked with. How many of you don't know what an MNIST data set is? You've done 572 or 575 and you did not use a MNIST data set, right? In any of the assignments. Okay, it's fine. So it's an intro data set that many folks use. It's a handwritten digits. It's a black and white image for each handwritten. It's like a single digit in each image. It's 28 cross 28 pixels or 28 cross 28 matrix, 28 rows and 28 columns. There's a some cells have so every cell has an intensity, some number between 0 to 55, and it's a black and white image. So forget about the three dimensions. It's just a one-dimensional kind of array or 2D array actually. Yeah, it's an image with a class associated with it, which is the image, which is the digit in that image. Okay. Anyway, so you can kind of any questions about this, like in terms of it's a bunch of numbers and it's a three-dimensional array. Any questions? How many of you are comfortable with the word array? I mean, we have used arrays in Python, perhaps, but uncomfortable. Comfortable is fine. Okay. So think of it as and we'll actually see what three-dimensional arrays in the next lecture when we actually work with some specific models. For now, we just need a collection of numbers. If you want to think of it in a simple way, think of it as a vector. Okay, a collection of numbers organized with some index. Okay. Now so last bullet point is mostly talking about nuances with image data. Is that it could be the same object in an image, the same digit, maybe in the MNIST data set, or it could be the same cat whose picture you've taken. But depending on various things, the numbers that you actually log in that three-dimensional array can vary quite a bit. Right? It's the same cat or the same digit, but depending on from where you took the measurement, which is like take an image, take a snap of the object, location of light source, whether the object is a rigid object or a fluffy thing or something which can deform, basically. Whether there's an occluding other things in that scene, background, and there could be and variation across objects of the same category, like two cats. For example, both of them are cats. If you want to just classify them as a cat, but then they have very, very different numbers representing them, right? So numbers can change based on many things that that's kind of hard to avoid. Okay, you cannot really avoid it. Okay.
When we talk about the three-dimensional array,
yeah.
So is it like each data point is a three-dimensional array?
Yeah. Yeah. Each data point is it. So we only talked about a data point. Yeah.
And the number of data points like rely on the pixel, number of pixels in that.
No. Number of pixels is actually each pixel. So pixel is, just think of it as a cell. Like let's talk about black and white images, right? It's easy to, especially if you work with MNIST data. If not, think of it as a black and white image is a matrix. Okay, either it's some intensity value. If it's 0, it's black, and if it's 255, it's white. Okay, so some number between them means some gray value, and so that's a black and white image. And so a pixel is just a cell in that two-dimensional image. Okay, and each image is a data point, and so you have many images, with each image having tons of pixels. Like MNIST, each image has 784 pixels. Okay, 28 times 28, whatever. But that's one data point. Okay, and you have potentially in MNIST you have 60,000 or whatever, some number of data points. Okay, in fact, that's my next slide, which is that three-dimensional thing, and the number of pixels there is just one example. So I'm going to use the word example, just to kind of not confuse with the word sample. If you have done statistics, sample can have a slightly different meaning. So we can have capital N number of training examples. Okay. So each one will generically represent it as X little I for the actual data, like that could be the image, and YI is a representation for the class value. Okay, it could be categorical, it could be numerical, whatever it is. Okay. So generally we'll represent, okay, this is my training data, Xi is the feature vector. Here I'm saying it's a feature vector, it could be the image, and then maybe you did some feature engineering to say, okay, the overall intensity of this image is high. Maybe it's a class 1. Maybe the overall intensity is low. Maybe it's class 2. You could feature engineer and create features, right? So let's, for simplicity for this slide's discussion, and actually next couple of slides, let's say Xi is a feature vector for the ith example. Okay, it's a vector for the ith example, and Yi is the label for the ith example. Let's say the label is also encoded as 0, 1, and 2. Okay, so let's say it's cat, fox, and a chair. Then cat is 0, fox is 1, and chair is 2. Okay, doesn't have to. You don't have to encode it that way, but that's one way to represent categorical things, right? You can just map it to some numbers. So before deep learning, as I said, if you had an image, for example, you would do all these things to get to that feature vector. You would, there are many ways to compute all sorts of functions, all sorts of some summarizing features for the image. Okay, for example, whether the image has, how many edges does the image have? Does the edge curve? Things like that. Many different features you can define based on your domain knowledge about the type of images you're working with. Okay? We'll not actually really get into them, but they are just, think of them as input is an image, output is a number, and that's a feature computed from that image. Okay, and you would have many such functions, carefully designed, lot of domain knowledge, and then once you collect those numbers, make them into vector, and then you get a vector like that. Okay. Turns out that deep learning, you don't have to get to a vector. You can actually kind of work with the tensors themselves or the three-dimensional arrays themselves. Okay. I mean, there's no big difference between a vector and a three-dimensional array. A vector is also a degenerate three-dimensional array. Yeah. So we will see that as we move along, maybe next lecture and so on. Okay. But you don't have to do these to get to kind of a good performance. Versus some of the older technologies, some of the more traditional technologies, let's say, they may need these to get to a vector so that they can actually do their operations on it. Okay? So the the ImageNet challenge that I showed, these types of transformations were done, and then you do an SVM based aggregation, or basically based classification to get to saying those 1,000 classes. Okay, that was the 2010-2011 solution, and then AlexNet, which is a name I'm just throwing around, but AlexNet was a solution that would directly work with the input tensors and not really think of these explicit features. Okay. So let's actually now shift to models. So this is just a recap. Okay, so that's why it's a little bit boring to some of you, perhaps. So we talked about data. Let's talk about models. There are many types of models. Model classes, actually. When people say model classes, think of it as a model class. Just means a definition of a model without setting specific numbers to the model. Okay, so a model is just an element in a model class, like a collection of models. So for example, when I say a model class, I mean like a linear model class. I'm not specifically saying what are the exact coefficient values, and that's why I'm saying it's a model class. Because if you explicitly say what the parameters are, then it's a specific model, specific instance. Okay. This distinction, so many ways to slice and dice different types of models. Whether something is parametric and non-parametric. It just means that parameters don't scale as a function of the data set, versus in some other situations, you could scale the parameters as a function of the number of data points. Okay, so and in this pretty much throughout the course, we'll look at pretty much parametric models in the sense that our models don't increase the number of parameters just because we got 10x more data. Okay, so and within parametric space, some people also assign some new names to certain special parameters, and we call them hyperparameters, but they're just additional things that you need to choose to completely nail down your prediction model. Okay, so maybe think of hyperparameters as some extra numbers that you also further need to tune or optimize, basically, but you still need to choose them, and that's why maybe they're chosen in a second stage or after you choose the parameters, perhaps, and so that's why there's a little bit of distinction between them, but they're all things that you need to choose to kind of nail down your model. Okay. So let's use. So in this slide, we're just giving an example model that everybody should be aware of, which is a logistic regression model. Okay, and you might not have seen it in this way, but this is a logistic regression model, which is the second one. Was it?
What did you say?
Logistic regression. Have you heard of logistic regression?
No. Actually, you were saying something I didn't understand.
Yeah. So I'm just saying that we'll give some notation to the model definition first, and then we'll give an example, which is a logistic regression model. So I mean, this is not a really general notation. This is just a notation that I'm kind of specializing because I want to say this model first as an example. So a model is nothing but it's a function, right? So if since you're all Pythonistas, so you can just say def function and then take two arguments. And generally, maybe one argument if you want, which is the thing that which you want to classify, right? Where you want to make the prediction. I'm just saying the second argument is the parameter of that model. So in that sense, the function that you're going to define is the model class, model template, and then first argument is if you could fix the second argument, which is the model parameters. In this case, I'm saying W and B are the model parameters. Then for any new test data, you can always say what's the return value as class 1 or 2 or 3 or 0, 1 and 2, right? So I want to introduce some vector notation, mostly because it's going to be useful for kind of the way we think or way we write deep learning models and train them. Okay, so it's a good idea to recap linear algebra. I know it's been told for when you did 572 or 575, but it's also good to recap that because it's good to you'll see that much of the actual calculations that you'll do is matrix vector multiplications or variations like that. So it's good to know that. So let's say X. In this example, since we want to work with logistic regression, X is a D cross one-dimensional vector. Okay. Okay, we'll see if the dimensions match up. But X is a vector which has D components or D coordinates. W is a parameter which is a matrix. Okay, W and B together are the parameters. One of them is a matrix, one of them is a vector. Okay, and now I wrote it this way, but in general, the function could be f of x comma parameter could be theta, for example. I wrote it this way because I wanted to kind of introduce you to the logistic regression model, which is actually just a linear model. Okay? This is a linear model. F of these arguments is nothing but the matrix multiplies with x, and you add an offset vector. Okay, so so why logistic regression? The story is not complete. Only when you choose a loss function together with this linear model, they kind of define the logistic regression, I guess, setting. We'll change this later in the sense that we'll change this function later. In particular, we don't have to have explicit w, explicit b. Could be any any number of parameters or any parameter set. So what's going on here, right? So a vector multiplied with a matrix is another vector. Vector plus vector is another vector. So f, when given an input vector, is producing a vector, okay, as an output, right? That vector of outputs, let's call it scores, okay, and we're going to call it scores. We'll see why we're calling it scores later. Any questions about this and why? So first of all, have you seen logistic regression? So okay, firstly, let me disambiguate that we're talking about logistic regression in the multi-class setting. So if you're thinking of in the binary setting, logistic regression, you would not explicitly think of it this way in a matrix vector type of notation. So we're looking at the multi-class logistic regression setting. Okay, let me just say that. Now, how many of you kind of remember logistic regression not defined this way? or is everybody okay with logistic regression? Yeah. Seeing it this way, that's because we've not defined the loss function yet. Okay, and so when people introduce logistic regression, especially they start with a binary logistic regression case, and then they'll talk about logistic function and so on. We'll see that the logistic function comes in the next slide when we define the loss function. Okay. Okay, at least okay. If you don't want to map it to logistic regression, let's say this is the linear model. Okay. But how do you use linear model in a classification setting? Right now, this is a function. This, there's a bunch of numbers. It's producing a bunch of numbers. Those numbers could be real numbers, as in they may not be corresponding to the class numbers or labels that we said 0, 1, and 2. Right. So we have to somehow get back to class labels and then qualify whether they're actually correct or not. Right. So we want to set the loss function appropriately for this model for the classification setting. So we still have to do that. Right. Okay. So let's first at least figure out, since this function produces a score, it produces a vector of scores. So what should the vector dimension be, right? So that vector of scores would be one score per class. Okay, that makes sense. For a linear model, if there are 3 classes, maybe it produces 3 numbers. And what we can do then is take the index with the highest score. That's how we convert that linear model to be able to do a class, to be able to tell me what class the input is, right? So if I have this function f producing 3 numbers, let's say cat, fox, and the chair example that I started with, then you just need to say, okay, the 3 numbers that were produced for this given input x. Out of the 3 numbers, which of the numbers is the highest, and what is the index of that number? Maybe that's my class. Okay, is that? So this is just a shorthand notation to say what exactly I said in English. So it's not important that you need to know the shorthand notation beforehand, but at least the thing that I said in English, you should be fine with that. Okay, so notation and stuff, you can get familiarized with it over the course of time. Okay. So does everybody follow what I'm saying? If you have a linear model, which means it's going to produce numbers. Remember, if it's a matrix vector multiplication, the matrix could have arbitrary numbers. It doesn't have to be integer numbers, right? It can have 3.2, 5.6 in different cells. And if you multiply a matrix with a vector, you can get numbers which are not going to be integers. Okay. So the way we set up the linear model is that if we have 3 classes, then we'll create the W matrix, the number of rows to be 3, such that we get the function's output to have 3 coordinates. Okay, 1 number per class. Okay. Actually, here I just said this P here is the number of classes, which is 3 is what I've been using. Okay, B is an input. It could be any any dimension that if it's an image, if it's an MNIST image, if you vectorize that image, it's 784 dimensional vector. but the output has to be MNIST is like a single digit classification. There are only 10 digits, so it's a 10 class. So P would be 10 in that example. Okay. But the linear model would produce 10 scores or 3 scores, and then one of the scores should be high, right? So hopefully the linear model is saying, hey, if it's actually a cat, then maybe the first coordinate should be the highest score, and then we're just speaking that, okay, since the first coordinate is the highest score, we're gonna say that that's my index. Index of that first coordinate is like 0, and so my class is 0, and so you map it back to, okay, 0 means a cat, so let me say it's a cat, right? So that's how I'm mapping back from numerical computation to class label. Is that clear or is it confusing? Okay. Okay. So instead of just looking at scores and taking a number, we can also transform the scores to numbers between 0 to 1. Okay, that's just a convenience. Is basically what you call as normalization step. You want to recenter. Okay, which means that, as I said, right. So this F produces 3 numbers in my 3 class example. Those 3 numbers could be going from minus infinity to plus infinity. Like it could be -1, 10, and 35.5. Right? How do you kind of recenter them? Right? So for that, you need a function that can transform those numbers all over the place to a number which is between 0 to 1. Okay? And this transformation, for example, is the sigmoid transformation. Okay, we'll see that again actually next lecture, but this is the okay. So, but for now, what we've done, we understood a little bit of the data. We understood, okay, how is the model represented, at least symbolically, and we're gonna kind of reuse this some of this notation sparsely, but we will still reuse them. So it's good to kind of understand it. And so what we're going to do next is, once we have defined, okay, this is the type of model, like a linear model, then what we need to do next is figure out the best choices here for W and B. Those are the things that I need to decide. And then once I fix those W and B's, then I can give that function to an end user and say, hey, now pass any X, you'll get a class, and hopefully the whole thing will work, right? So to define what's the best choice for W and B, I need to choose a loss function. Okay? And to find the best choice, once I define this, I need to do computation, and that computation we're calling it as optimization. That could be trial and error, it could be us just randomly choosing some numbers, or it could be computers trying to get to the best choice. Okay. So let's look at loss functions. So for that, again, let's stick with the narrative that this function f produces scores. Since we're in classification setting, let's say 3 classes, it produces 3 scores. Okay, the score in the jth coordinate is called, let's call it Sj. Okay, so S S0, S1, S2. Okay, and we're going to use this F to define loss function, which is the quality of our current parameter choices. If we had a choice, okay, let's put W to be a identity matrix. Okay, why not? Like, if I chose the W to be an identity matrix and the B vector to be all zeros, then what is my loss? Right? What is my loss? Loss is just a number that I'm associating with this choice of W and B, which says how good those choices for me to do my classification. Okay, maybe it's terrible, the choice of an identity matrix and zeros as B vector, but that terribleness is captured by the loss value. And how do we do that? So for that, we use the model, the choice we made, and the training data set. Remember from the data set part. So we'll use those 3 to compute this number. Okay, how good the model, the current choice of the model parameters are. So how do we use the training data? So first, let's decompose the training data. We have n of them. So how do we use all of them? We're gonna do a very simple decomposition. So we're gonna say, okay, let's compute this quality score by first saying, okay, the quality score is just the equally divided, equally aggregated score from each individual training example. So L data, which I'm calling as this quality score or loss value, is equal to 1 is equal to this, again, it's a Greek symbol sigma. Okay, it's just a summation notation. Again, the notation is not super important. You should know at least the English meaning of it. Just sum over all examples, I is equal to 1 to n, and there is a loss value that I can associate with each example. Okay. So here's some example loss values. Loss choices for Li. Okay, since we already said okay, this is equal to we're gonna say what is the loss value per example. Let's focus on what is for a given example, what's the quality of my model. Okay, my model means I've already specified what the W&B, like some candidate generic W&B is already specified. Okay. Here is the loss that completes the picture with the previous linear model. This loss with that definition of function is a multi-class logistic regression model. Okay, so this loss is called logistic loss. It's also called cross entropy loss, which may be new, but may not be new, but it's also the same thing. It's the same thing, and it's also called the softmax loss. Okay, it's all the same names. But let's look at and we'll see why it's called that over the course. Okay, so I know this first lecture is supposed to be recap, but some new terms are being shown. But the example, for example, Li for this definition of this loss is going to be negative log of what we're going to call as probability of the label being y little I. Okay, this example I, we already know it's xi comma yi. So I know for the label for the example xi, I also already know the label yi, right? So it's saying negative log of the probability that the model is assigning to this label, okay, maybe the cat label, given the cat image. So for this ith example, maybe it's a cat image and a cat label that's there in the training data. The question is, what is the model assigning to this label? Because remember, the model is actually producing scores for all three labels: cat, fox, and chair. We're asking, okay, what is the value that you're producing for the
that was the index value, right?
Was it?
That's what we define as.
Yeah, you can think of yi as 0, 1. Y is to be values 0, 1, and 2 if you want, or you can also call them actually cat, fox, and cat, fox, and chair if you want. Yeah. So what is this probability? Like, where did the probability come from? Like, we did not even talk about probability when we're talking about models, right? The model is just producing three scores, okay, three numbers. This probability is actually a convenience that we are kind of defining. We are it's a user-defined thing. The probability for any coordinate, like any label, like 1, 2, 0, 1, and 2, given input is going to be a transformation of the scores. Remember, we said we wanted to do transformation so that we kind of normalize things to be between 0 to 1. So we just chose, okay, since it's a linear model, it's producing numbers between minus and infinity. Let's actually compress them between 0 and 1, and let's normalize it this way. Okay, so we have those three numbers S0, S1, S2. We're going to say, okay, first number is actually, it's S0. We're going to transform it this way so that the new number is going to be the probability instead of that original S0. Okay, so this is called a logistic transformation, okay, or a softmax transformation, and that's why I guess the loss function's name is logistic loss. Okay. Yes.
I'm a little lost on the part where is this making a decision based or like classification based on every single pixel of this image, and then
that's a good question.
Over the picture with all those pixels, and then aggregating all of the training samples. Is that what it's doing?
We're not doing class. We're not yet making a. Okay, let me phrase it properly. So we have. Yeah, it's a good question actually, and if you have this question, then other people may also have a question. So think of X as the input, right? For this exam, for this few slides, I'm just recapping classification. So I didn't want to explicitly talk about a three-dimensional array. Okay. So I said X is actually a vector. Now, if you have pixels in an image, right, whether it's a black and white image or a color image, if you really want to think of them as a vector, just concatenate them or like vectorize it. Okay, you've done vectorization operation of matrices, you just concatenate column by column or row by row, just expand it. In fact, for MNIST data set that we're talking about, which is like a tutorial exam, a data set that people use, one of the ways to build a classifier, the first time is just vectorize your images, and that 784 dimension, because it was a 28 cross 28 pixel size, that vector is your feature vector. Okay, that's your input. And then for MNIST, since there are 10 digits, there are 10 classes. So you will produce 10 scores. So this linear model is going to produce 10 scores, given that 784 dimensional vector. Okay, if you can get the right parameters, these are the parameters of the model that you need to tune using training data. And to do that, we need to quantify what is the quality of W and B that I choose. Okay, and that's where the most important step that I'm going to discuss next is going to come. But since the model is producing scores, which are those 10 numbers, if you're thinking of MNIST, I'm just using the MNIST so that everything is standard. It's producing 10 numbers. So one of the numbers, whichever number is the highest, it's very intuitive, right? Well, whichever number is the highest, that's what I'm going to interpret to be the class of my classifier, if W and B are known. Now the question is, what is the quality of W and B? And that's what we're trying to define to get to, okay, different W and B pairs will have different qualities, and I want to pick the W and B pair which has the best quality or the lowest loss. Okay, we'll do that with some extra bells and whistles like cross-validation stuff later, but let's actually do that. And for that, if you're going to stick with multi-class logistic regression setting, we've already defined the linear model 2 slides ago, where F was just Wx plus B, right? Given that model definition, the linear model, if you use this log function, so negative log of this softmaxed version of the scores, remember the scores are actually each coordinate of the F function. So F produces the scores. Once scores are produced, you just transform it this way, and then you pick one of these numbers. So which number? For that example, whatever is the true label, right? Let's say that input example corresponds to the digit 5. Okay, so then you look at the 5th or 6th coordinate, however you index it, and then look at what is the probability that the model is assigning to that coordinate. Okay, so the intuition is, if the model is saying that data point is of digit 5, and so if the model is saying if the model can give a high score to that coordinate, so if the image is 5 for the number 5, then for the 6th coordinate, let's say, if the model gives a very high score, then this probability is going to be super high, because if the score is high compared to everybody else, this transformation somehow ensures that this probability is going to be super high, very close to 1. Okay, log of 1 is kind of close to 0. Okay, log of a number a little bit less than is actually slightly negative, but let's say close to 0. And the negative log of that is something which is just flips the sign so that it's positive. Okay, remember, log of a probability numbers are always between 0 to 1. So log of probability is always going to be negative. Okay, we want to make them as so the negative sign there is ensuring that you get to positive side. And if you make the actual probability, if the model is actually good and assigns for the digit 5, the coordinate 5 to be the highest score, then this negative log of this thing is going to be as low as possible. But at least for that example, the loss values, the Li is going to be very small. Okay, and if the model actually does well on all the training data points, then each of the LIs is going to be small. So the overall Li is going to be really small. Okay, we want the loss value to be small. Okay, but think of the other situation where the model for the digit 5 produced a very low score for the coordinate that corresponded to the label 5. Okay, if that's the case, then it produces a low score. So this probability is going to be low, because remember, scores are directly proportional to probability in some sense. It's going to give a low probability. Low probability value means log of a number, let's say low probability is 0.1 or something. Log of that number is going to be a huge negative value, and a negative sign in front flips that to a huge positive value. So the loss is high if the model performed badly on that example. Okay, does that clarify? We haven't fully completed this picture yet, but what's left is just talking about how to get to the best parameters. But here we are not yet talking about the best model yet. For any model, you can compute this quality score. I'm calling it quality score. Just think of it as loss value, right? For each model, there's one number per model. Obviously, you're not going to enumerate for every model, especially if models are not enumerable. In fact, even linear models, there are too many of them, right? You can't say what is the coefficient, what's the coefficient, what's the coefficient. You can write it to discretize the coefficient and so on, but conceptually that's what's happening, right? You have more questions? No. Anybody else have any questions? Okay, so what I'll do is not talk about SVM loss. It's again, if you understand this intuition of why the model should produce a high score, and if it produces high score, the loss on that example is small, you can understand this interpolation. That's actually important for for now. Obviously, if you're still hazy on it, try to pass this, at least this example at least afterwards. Okay, and this has huge connections to other things. Okay? The moment you say negative log of a probability, this is called the negative log likelihood as well. Okay, and now generally what you want to do is minimize loss, right? And so you're minimizing the negative log likelihood, which is the same thing as maximizing the log likelihood, and that should connect to all the maximum likelihood estimation and other things that you might have seen. Some of you might have seen in other branches of statistics and prediction and so on. Okay. So this is that. So typically, loss functions can be interpreted. Sometimes they cannot be. For example, there's no interpretation of a probability or anything for the SVM stuff. But at least for logistic regression, you can interpret this as kind of essentially maximizing likelihood. Okay, we're maximizing likelihood here. But we define what probabilities is, and it's not it's not like starting from first principles where we had distributions and then we had a likelihood, but nonetheless, that's what it is. So let me actually wrap up loss functions and take a break first. So we need one more thing, which is we don't always need it, but sometimes it's helpful. Is the idea of regularization. Okay, regularization again is a informal bucket where you kind of want to impose prior knowledge or preferences or anything that is not informed by data. Anything that's not informed by data, and you want to capture that in some sort of additional quality metric, just like loss metric. Loss is a way to say, hey, is the model good or not? Similarly, an additional metric which can say whether the model is good or not, but the additional metric doesn't depend on data. Could depend on your preferences. Maybe you want a sparse model, like a sparse linear model just means most coefficients of features are 0, some coefficients are non-zero, or you have some preferences like that, then you can capture that using this umbrella term, regularization. Okay, so why do you need regularization? Sometimes there could be many models which all have the same loss metric. Okay, there could be too many models. Like let's say there are 2 models which have the same L data, the term that we saw in the previous slide. Then which one do you pick? Okay, you have the express preference, right? Or you can always flip a coin and pick one of them. Or you have a preference of what types of models, like sparse example that I gave. Or you could also say we want to control overfitting, and that is again overfitting just means that we are able to fit really well on the training data, which is the data that we use to define the loss. Here, we get really good value, L data value, and really good as in sense really small value. But it turns out when we actually give it to the end user is seeing like very bad results in the sense that a cat is being classified as a chair, or a chair is being classified as a dog, or something like that, right? So that is something that we want to control. So maybe we want to impose regularization. So generally, you would see in various textbooks or various places, you would have a thing that depends on data and things that don't depend on data. Things that don't depend on data, you can just call it as regularization, or some extra preference or domain knowledge or something that I'm imposing for imposing towards the quality of my model. So these are obviously functions of the parameters of the model, but they don't depend on data. Okay. So here I'm using the Greek letter lambda to just linearly combine them, which means that this is a number, and let's say this regularization is also a score, so it's a number that I'm assigning to every potential candidate. So a non-sparse one will have maybe a high value, and a sparse model, which I prefer, maybe having a low value. I just want to combine them. I can just add them with this lambda value equal to 1, but instead of that, maybe I want to upweight. I would want to trust the data more, then lambda is going to be small. If I want to trust myself more, or whatever, not the data more, maybe lambda value is high. Okay. Okay. So let me start here, which is here are some examples of regularization. So just these are functions that you might have seen. It's just if W is a matrix, remember, it's matrix means there's a bunch of rows, bunch of columns. Every row column combination has a number there. L2 regularization just means take each number in each cell of that matrix, square it, and sum over all the rows and columns. Okay, just take every number, square it, and then add it. Okay, so that it's positive. There's an interpretation for this. I think in 572 or 575, people interpret it sometimes, like some Gaussian regularization or something, Gaussian prior. L1 regularization is just a name. These are all definitions, by the way. It's just if you take the absolute value of each number and then sum them together. Again, you keep it positive. I think in 572 or 575, there's a lot of time spent on interpreting this as giving you sparse solutions, preferring sparse solutions. Sparse just means a lot of Wij's will be zeros, and some of them will be non-zeros. Is what you prefer. If you prefer that, maybe impose this regularization. Again, there's no direct. I'm not explaining how this regularization is going to give you a sparse solution. That we are skipping here, but this is an example of a choice that you can make. And then there's a combination of them. Where again, I'm using the Greek letter alpha to just do a linear combination. Actually, yeah, a convex combination, but it's still a linear combination. Just combine those two preferences. This is all review. So if you've not seen it before, no, it's not super important. But if you have seen it, just connect it back to regularization is an important concept from before. Okay. The other regularization ideas that we'll actually see in this course, which are not typical, not something that you've seen before. One example we'll see is called something called dropout. Okay, we'll see that 3 lectures from now, 3 or 4 lectures from now. So let's take a break for 10 minutes and resume at 5:13. It's 5:03 now. Okay, so I just wanted to show actually I want to show an example later after we go through the classification review. We have still optimization left and then backprop left. But before that, I just wanted to show an example of importing an image, right? So there's a couple of extra steps because I'm importing directly instead of saving it on disk. I'm just importing it directly from a URL. So I just like this is my website, right? I can just load my image, or you can get so the name of this Python imaging library, also called, I guess, Pillow, is a fork of that. You can just make a response, a HTTP response request, basically a request response, sorry, and get that image. Okay, so this is one way to kind of read an image. So here actually I read that image. It's in a particular format supported by this library, and then I imported a package called Torch, and we'll talk about Torch in the context of backpropagation in a few minutes. But if you already heard about it, it's like scikit-learn. It's a very good toolkit to know about. It's like NumPy, actually closer to NumPy perhaps than scikit-learn, but it's a good package to work with tensors, as in these 3-dimensional arrays and so on, and does something really cool which NumPy doesn't do by itself yet, which is backpropagation. Okay, behind the scenes, there's some really good behind the scenes functions that get triggered, and they can do backpropagation for you whenever you want it. Okay, and we'll discuss that later. So with Torch, but the purpose here is just show that you can transform that image, which was in a different format. You can actually look at what functions are available in that library, one in the image object. But it's just an object. Okay, it's some object with a bunch of functions and values or fields. You can transform it, and then if you look at the shape of that image, this particular image is my own image. So it has 3 cross some 1,000 pixels cross 1,000 pixels. So it's like a 1 megapixel image and has 3 layers or 3 matrices. As I said, like one would be for red, one would be for green, and one for blue. Doesn't have to be only in that combination. You can actually, there are many color formats, HSV and other things. But so this is the matrix. Okay, so if you want to extract one layer, or one matrix, then you can just index exactly how you do it in NumPy. It's like indexing is very similar to NumPy array indexing. Okay, so hopefully this kind of clears the confusion about this, and you can vectorize it exactly how you do in vectorize in NumPy as well.
Okay. There is 2 tensors compared to the 3D array. They create a 3D array. To get some in a format where I can do just NumPy type of operations. I'm sure, like I was just looking at, like, for example, there are a lot of functions. I mean, this is my way to get the functions, but I don't know where the image data is stored that I can just see. Maybe it's stored. So this object, the original image object, the original image object is from this, right? So it's a Python imaging libraries object for an image. It has a lot of helper functions, but I don't know if natively it exactly stores it as like a 3-dimensional array itself. Maybe it does. I need to look at which
of these fields actually corresponds to data. I see get data here, but yeah, I see get data here, but I don't know if the data is natively stored somewhere as data itself. Okay, let's not worry about that. All I'm saying is, if you want to play with images and see what numbers they are, like MNest also, you can load it here and just get a feel for, oh, it's just a 28 cross 28 pixel image. Okay, it's just a 2D image. Let's come back to. Sorry. Yeah. Am I sharing the screen? Yes. Okay, so what we've left, we were just recapping classification right before the break for maybe 30 minutes or so. We started with data. Okay, there are different types of data. The typical one would be a vector. Like if you think of an Excel sheet or a CSV sheet, one row of that sheet would be a feature vector. And if you have, whether you have categorical values or ordinal values or integer values or numerical, regular, real valued numbers, whatever they are, like it can be a vector. And you, at some point, you want to convert all of them into numbers, because now we're going to multiply them with matrices. So if you had a categorical variable, you can assign some, there's different ways to encode or transform that categorical, column into numbers, right? You can say, okay, if there was a categorical column saying, is an animal or is not an animal, okay, maybe explicitly as a string, you can just change that into a 0 and 1 value. And there are many ways to do it, and we'll see other ways to do it later. But we wanted a vector X which had all numbers for the previous discussion. Okay, just to clarify, because we wanted to multiply that vector X with that matrix W and then add another vector B to get my scores, the 3 scores for the 3 class example I was talking about, or the 10 class example we were also talking about MNest. Now let's talk about optimization. Okay, so we had the model. We have the data, we kind of talked about a little bit about the data. We have a model specification, and now we want to figure out what is the best parameters. And define the best parameters, we define what is called a loss function. The lowest value, or the L total, or L, which is a part of L data and the regularization term, both terms, both subcomponent metrics together compose, together add them up together with some weighted combination, giving you the L or the loss. We want to have a model with the lowest loss. Okay, let's start with that. How do we get that? Okay, so because the loss is what's quantifying a model, we want the best model, best in terms of the lowest loss. Okay, that's as clear and quantitatively as it can be. Now to optimize, I just want to show you what are the moving components, right? So this data was used to compute the scores. So for a given W comma B parameter, given all these examples, I can get the scores. These scores together with the label, you can get the definition of L, right? You can get the L value, right? Because all these scores can be transformed to get the probabilities, and probabilities with the true labels. You pick the right probability to use in your negative loss, likelihood function, or whatever the cross entropy term, for example, and that would be Li for each example, and then sum them together. That will be L data. That plus some regularization, if you want to add some regularization, will be the final score for that model choice, for that model parameter choice. Okay, so this is just a block diagram to say these are all the moving parts. Any questions here? Okay, so now let's, that W comma B was just because I had an example which is related to logistic regression, and I wanted to use that example because that's actually a neural network as well. I'll make the connection in a few minutes. But in general, you can have parameters just represented as theta, like the Greek letter theta. Okay. How many of you are not compatible with Greek letters? Like that I use. Like otherwise, I'll explicitly explain it. Otherwise, I can just not explicitly point them out. We've used the sigma character, the theta character here, the lambda character in the previous slide. So if you come across something that you've not seen, we can just debrief. It's just a shorthand for explaining something in English. Okay. And this hyperparameter was the one adding the L data with the regularization. Okay, so that's the block diagram, and we want to get the best W comma B. How do we do that? Okay, so it's a we know what best can, like, for every candidate model parameters, we know what its quality is or what its loss value is. We want to get the model parameter pair, or candidate pair which has lowest loss value, L value. So that's a search process. In some sense, you want to find out in the space of all W comma B pairs of values that I can have, what are the values that lead to the lowest value, okay, lowest L value, sorry, right? So it's a search process in one way. To do that search, what we're going to do is a iterative process. Okay, we're going to do an iterative search. So what is iterative search? We start with the candidate W comma B pair, and then we try to improve it. Improve in what sense? The current W comma B pair will have some L value associated, loss value associated with it. We hope that we can get another W comma B pair, an iterative improvement, or one-step improvement, such that the new W comma B pair will have a little bit lesser loss value, if possible. Okay, and maybe the next iterate will have a little bit lesser loss value problem. And hopefully, after a lot of iterations, we are not able to make progress, which means that if we try to do some other, get to some new iterate, it's either increasing the loss value or it's not, it's not decreasing the loss value in some sense. So we stop there. Okay, so that iterative process, we can do that using gradient descent, and for that we need to understand what a gradient is. So this is just one slide recap of what a gradient is. There are many ways, just to give a sense. So this iterative process is not the only way to get to search for the best model. Okay, there could be non-iterative ways as well, but let's focus on, for example, for linear regression, right? So for the vanilla linear regression case, you guys know you don't need to do this gradient descent based iteration. You can just do the matrix inverse times, like I don't know if you remember, if y is equal to x times what are the parameters, like beta? Let's say let me use some numbers which I don't know if you remember this. Y is equal to x times beta, then there's an x times x transpose x inverse, x transpose y or something like that. So, I don't want to get into that detail, but because it's weird, I don't want to introduce new notation. But you can literally do some matrix inverse if you want to solve at least some linear equations, right? Ax is equal to b, which is what a linear regression model looks like. Then you can just do A inverse b essentially. To get the value of the unknown. So you could do non-iterative things also, but we'll focus on iterative approaches. And one of them, and these iterative approaches, one class of such approaches are called first order methods. Okay, and we'll see why it's called first order methods. But they're called first order methods because they exploit what is called a gradient information. Since gradient is something essentially equal to first derivative, they're called first order methods. If you are using a second derivative to do this iteration, then they're called second order methods. Okay, second derivative, it's also called a Hessian, but we will talk about that later. So, okay, what is the gradient, right? So gradient is a vector with the same dimension as, okay, so let me first fix something. So let's say you have a function of an argument. Let's say the input is z. Okay, let's say z is one dimensional for simplicity. Then a gradient is also a one-dimensional number. If z is 10 dimensions, 10-dimensional vector, then gradient is also going to be a 10-dimensional vector. Okay, so gradient is just a vector. Okay, it's the same dimension as the input to your function, which tells you how much the function value changes if you change. In each coordinate, it says how much the function value changes if you change your current input by a small amount. Okay. So this mathematical notation, if you don't want to focus on the notation, all it's saying is that a gradient is defined at a current value, okay, a current location. Just means that at the current input z, okay, let's say it's a vector, I have some value of this function. Okay, it's producing some number, let's say 10, like our loss function, right? So current value parameters is producing some number. We want to ask if I slightly change my current parameter value, slightly change it. How do I slightly change it? For, let's say my parameter is the W and B, right? So every number in W matrix and every number in the B vector is a parameter. If I slightly perturb them, the function evaluation will change. The loss value can change, right? The question is how much is the change? You can just subtract the change, the value, the new value minus the old value, divided by how much change we added, right? So z and z plus h. So h is the change that we added. Now this makes sense for one dimension because I divided by h doesn't make sense for a vector. So in one dimensions, let's first intuit it. In one dimension, current value, whatever the value is, if I had a slight perturbation, it is the function is valuing some new value. How much did the function change when I change the input? Okay, that's what a gradient is in one dimension. So and in terms of if the input is a vector, then each coordinate, how much is the function change? Though that each coordinate will kind of capture what is called a partial derivative. Okay, keeping everything else fixed, in that coordinate, how much did the function change? Okay, and you collect all of them, and that's a gradient. Okay. Any questions about gradient? I mean, for this, you'll have to, I mean, I just explained in very suboptimal way, perhaps, but you'll have to just quickly review calculus to kind of get a little bit more intuition about gradient. This is the numerical way to compute a gradient, okay, in one dimension, and in multiple dimensions, as I said, you want to compute what are called partial derivatives, which is just if z is a 10-dimensional vector, focus on the first dimension, perturb it a little bit, and see how much the function changed when that was perturbed, and that's a partial derivative of f with respect to that first coordinate, and then you collect all the partial derivatives together. 10, there will be 10 of them because the 10 input is 10-dimensional, let's say, and then that's the gradient. Okay, you can do it numerically the way I said. You perturb it and track how much the function changed and look at the rate of change, basically. Or you can actually also use chain rule when it's available to you. Okay. In a sense, in some situations, you can actually just use chain rule to figure out, your gradient. Okay, your gradient of a function, which is the list of the vector of partial derivatives. Okay. So now let's come back to the iterative template. So we start with a candidate model. A candidate model just means a candidate parameter pair, W0, B0. Okay, W0, B0. Sorry. And then what we do is we evaluate the loss for this current parameter, W0, B0. There will be some number, let's say 10 units, 3.1 units, whatever it is, the cross entropy loss, for example, in the logistic regression case. And then we want to change W0, B0 to a potential new value, W1, B1, hoping that W1, B1 hopefully has a lesser, has a potentially new loss value which is lesser than the previous one. That's the hope for this. That's the idea of this algorithm. That doesn't always happen, especially in deep learning situations, but it can happen in some nice situations. And since it happens in nice situations, we can just use that same template in a more general, harder setting, which is deep learning. So, and then you just repeat. Okay, repeat just means you again start with W1, B1, evaluate L, and from W1, B1, you go to W2, B2 and evaluate its new L. Okay. So how do you go, right? So how do you go from W0, B0 to W1, B1 or W1, B1 to W2, B2? The intuition is actually the sense of gradient descent. How do you go from old parameters to new parameters such that hopefully you have improved, as in reduce the loss. Okay, you want an improvement when you go from old to new. Okay, and the intuition is actually which is this iterative approach is called gradient descent, and the intuition is that the negative of the gradient of the thing that you want to minimize, in this case loss, the negative of the gradient will lead you to negative of the gradient will lead you towards a direction where you can define a new parameter value W1, B1 such that will have a lower loss value. Okay. Yeah. So I don't know if I have an image. Yeah, let's look at the image first and then come back. So let's say this is no, this image is actually one-dimensional, so we don't have vectors. So gradients are not, in this case, gradients are not vectors, but just numbers. But let's say we have this function. Okay, this is the loss function. Okay, it's going up and down, but generally it doesn't have to go up and down. It can be a nice, like parabolic thing also, right? Generally, loss functions are positive. This is not really a loss function because it's going negative here. But let's say this is a function. I want to find the lowest point, right? So the way gradient descent works is that you start with some initial value of your input, and you want to descend through this loss surface or this function surface. Okay. Generally, think of this function as a loss function, although the offset, it's negative. How do you descend? You have the current value, and you want to take the gradient of the function value with respect to the current value. Okay. In this case, it's just the derivative of f with respect to the current value, whatever 0.5. Whatever that number is, put a negative sign in front of it, or basically multiply it by -1, and then just add that to the current value. And it turns out that new number is going to make you go left. Okay, that new number is going to be smaller. A new coordinate or new input is going to be smaller than the older one. Okay, in this case. Why is that? So the gradient of this function is just the it's basically the slope here. Okay. You can see the slope is positive, something like 45 degrees. So think of it as +1. And so if you put a negative sign in front of it, it's -1 essentially. And so the original number is 0.5, and you do add -1 essentially. And so you're not really adding -1. There's some scaling here, but you're subtracting something, and so you're going towards the left. Okay. But if you are on this side, let's say here the slope is, if you change a little bit of this input, the function is decreasing, right? If you add a little bit to the input, the function is decreasing, so the gradient is negative, and negative of that is positive, and so you add a little bit of positive to the whole quantity, so you go this. Okay. That was a very short introduction to gradient descent, but that's how you're making progress. Okay. And
suppose two arrows are gradient descent.
Two examples of, if you started from here, you go there. If you start from there, you go there. Okay, that's actually one. So this figure is actually showing a weakness of gradient descent, which is that if you have not nice loss functions, okay, like if you just literally plot the loss function in one dimension, it's easy to plot things like this, but it turns out even for logic regression, you can't plot this. Okay? The moment you have W comma B, and W is a 2x2 matrix and B is a 2x1 matrix, let's say, or something like that. So you have 4 numbers plus 2 numbers, you have 6 numbers. You can't really plot a 6-dimensional thing because you want to figure out with respect to W comma B, how does the loss function look like? But in one-dimensional case, this is the intuition. You start from somewhere, gradient descent lets you descend towards the valley of these functions, and generally we are trying to minimize the loss function, so you get to pretty much the lower part of the loss function. Yeah. We are not, right? So if we have a full picture, we can say whether something is global or local minima, but otherwise we cannot. We cannot give a certification of, let's say we did gradient descent, and we kind of got to a point where we're not improving. Okay. The question is that a local minima or global minima? Is hard to say in general, but for logistic regression, it turns out that there's only one minima, and that's global minima. Okay, so for logistic regression, it turns out the loss function, even though we were saying we cannot plot it, it basically looks like a ball in high dimensions. In one dimension, if you think of it, it's like a parabola. So it doesn't matter where you start, as long as you have made some reasonable choices in your gradient descent has one parameter that I'll show you in a second. You will get to the bottom of the ball. Instead of taking off like a rocket, you will actually go to the bottom of the ball. Yeah, but we can't identify this here. We're just showing that there could be multiple minima. Okay. Now let's come back to the approach. As I said, there are some parameters in gradient descent. Here the version, I guess, there's nothing batch about it, but let's say there's also a batching idea in gradient descent, which means that at each iterate, we don't want to compute the full loss value, because remember, if we have 1.5 million images, maybe it's hard to find, and they sum them together, right? And remember in the ImageNet classification example, maybe summing a million terms together every time you're making a gradient update may be too computationally expensive. So what people typically do, and it's just a rule of thumb, is that instead of doing, you get a kind of a proxy value for L by saying, okay, instead of looking at all 1.5 million images or 1.5 million examples at the same time, I'll look at like 1,000 of them or 50 of them or 100 of them. That's called a batch. Okay, instead of looking at the full batch of full data, you're only looking at a part of the data while taking a gradient step, and that's called batch gradient descent. So, for example, that model, that AlexNet from 2012 that had like a really huge improvement, it used 256 examples. So 256 images out of 1.5 million images. Okay, you may say, okay, this seems too low, but it helps with computation. At that point, the GPUs were not, did not have so much VRAM and stuff like that. Now you can actually probably don't need to do batching for that case. Now you want to get the gradient of the loss with respect to parameters and make improvement, right? That's what the template was. Now, how do you make improvement? Remember, gradient of loss with respect to parameters. That's why I wrote two equations, because I explicitly wrote two separate parameters W and B. But if there was only one parameter, let's say theta, then theta new is equal to theta old minus some term, some scaling constant. Okay, so this can be constant. This can also vary over time or vary over index or whatever iterations. But some scaling term, which is a parameter of the optimization algorithm, in this case batch gradient descent, times the gradient of the loss with respect to the parameter. Okay, so that's exactly what we discussed before. So you just take find the gradient of the thing that you want to minimize with respect to the things that you want to change so that you can minimize it, and multiply it with some constant. So alpha and beta are Greek letters here, and this is how you represent the gradient with respect to anything. And so these numbers, just think of it as like 0.1, 10 to the power minus 3, and so on. Okay. Yeah, so these are called step sizes or learning weights. Okay, many of this new names that you're seeing, we kind of will see it more, and so so don't worry too much. Any questions here? Okay, we just discussed that, and then gradient descent is not the only way, not the only thing that you need to do. You also need to set a few more things. Perhaps you have some additional choices. So for example, remember that lambda, that was the term that was kind of balancing the data term and the regularization term. Maybe you don't know what the right lambda should be, and you want to decide somehow like that lambda as well. That could be a hyperparameter. That could be called like hyperparameter. And then how do you choose that? There are many ways to choose that. Maybe just trial and error. You try 10 different lambda values, and whichever leads to low loss or on some held out data, perhaps just take that lambda. Here, this is something that you might have seen before, which is k-fold cross-validation, where what is the purpose of cross-validation? Okay, it's not so much about the purpose of cross-validation is about, okay, let me say, the use of cross-validation is to figure out choices of these choices, which gradient descent itself will not do. But what is cross-validation essentially doing? It's giving you a proxy for test performance. And that's what it's doing. So you need to make some choices, but you care about test performance, and you don't care about, you don't really care about training performance. So all it's saying is, here's the proxy. If you chose whatever hyperparameter value, let's say the lambda value, if you chose it to be 10 units, this is the kind of number that you'll see on test data. And if you choose it to be 100 units, this is the kind of number that you'll see on test data. That's what cross-validation is doing. It's just computing an estimate of test error. Okay. Yeah.
Perhaps the use of hyperparameters is the parameters you take already defined function class.
Yeah, the hyperparameters are not part of the function class.
Yeah, but what are they used for if they're not part of the function class?
Yeah, so let's actually go back here, right? So we wanted to so W and E are parameters. I also want to minimize. So I want to minimize this. I could actually just say, oh, I want to minimize WB and lambda. I want to take WB and lambda to minimize this. I can do that. So here, obviously, there seems to be like multiplication, but that's fine. The whole thing is anyway non-linear. So, but you could actually minimize, find the best choice of all three to minimize this. But cross-validation is just kind of saying, okay, let's not trust only L data. By doing this k-folds, it's kind of getting an estimate, kind of an out of sample estimate by saying, okay, train on 3 folds and get an estimate on the 4th fold, things like that. But it's just trying to let you choose lambda. Okay, but you don't have to choose lambda that way. You can do many things. Yeah, but all I'm saying is to completely finish your choice for like what is best, because the best is defined using lambda as well. So you need to figure out what's the choice of lambda, and then whatever is corresponding W comma B, then that would be your model, right? Okay, I think I took too much time in this space, but let me go to backpropagation. Okay, so the next last concept, yeah. as I said, it's chain rule. So how many of you remember chain rule? Okay, 2 on the side. How many on the side? Okay, so we can look at the Wikipedia article on chain rule, but basically, let's look at let's put it in the context of the example that we were discussing earlier. Okay, so I've used a little bit different notation here, but let's focus on. Let me explain each part of this diagram now. So think of this H as our H as our function f. Okay, in the previous slides. Yeah, I want to kind of ground it. So H is a function f. Let's say A and B are like the W comma B. I just made it A and B here for simplicity, but let's say this is like two inputs. Okay, this is what we care about, right? Remember, in gradient descent, the data doesn't appear. Data is somehow is part of the computation, but we don't care about the gradient with respect to the data. We care about the gradient with respect to the parameters. So A and B are kind of equivalent to W and B. Let's say this is the prediction function, and then the prediction function led to some intermediate computation. Let's think of them as scores, and then the scores led to some value, loss value. Right? Let's call the loss value G. I didn't explicitly show it here because this is not tied to the previous thing, but let's say the loss value is G. Now you want to find the gradient of G with respect to the actual parameters of the model, A and B or W comma B, whatever you want to call it, right? We want to find the, remember, gradient of loss with respect to the parameters. So how do you do that? By chain rule, what we do is we first find the gradient of loss with respect to its inputs, okay, which are scores, okay, and then we find the gradient of the scores with respect to its inputs, which is A and B, and then we multiply the gradient of multiply these two local gradients together to get the gradient of the loss with respect to parameter W and B individually. Okay. So what is chain rule? So if we want to find the gradient of the loss or gradient of G with respect to A, first we find the gradient of G, or actually I'm using the word incorrectly, the partial derivative of G with respect to intermediate quantity H, and then the partial derivative of H with respect to quantity A, and then multiply them together. That's the chaining process. It's just so if you want to compute the overall gradient or the overall partial derivative, you can just find the partial derivatives of the intermediate computations and just multiply them together. That's it. That's chain rule. Okay. It works nicely for any function. In fact, there's an example that we'll go through in a minute. But this is just showing that you can just focus on any computation in between. Let's say this is since we said there's a prediction function, there's going to be some incoming gradient. Remember, chain rule, we have to multiply something, so we have to think in terms of some linear computation process. So there's going to be some incoming gradient, and there's going to be some local gradients. Okay, local gradients means I just know what my output, how much my output varies with respect to my inputs. That's local to me, local to this function. It doesn't need to know what the loss function is. Okay? As long as some loss function is going to give me, how does it vary with respect to its inputs. Okay, I can just take that, multiply with my local gradient, and pass it back in case it's needed for further. Maybe A and B are not the parameters themselves. Maybe they're transformations of the parameters. Then you can keep going back. Okay, that's chain rule. Okay. Any question here? Okay, so so we're propagating partial derivatives. These are partial derivatives. This is a partial derivative G with respect to H. Okay.
So that is a partial derivative within of H.
These are local partial derivatives. Local in the sense that as long as you know this function, you can tell me what is the partial derivative H with respect to A, partial derivative H with respect to B. Okay. Somebody else.
Value of H.
How much H varies when A varies, how much H varies when B varies. That's what it is. Yeah. Those two, if you put them in a vector, that's called the gradient of H with respect to its inputs. Okay. If inputs are two-dimensional, gradient is a two-dimensional vector. So let's look at an example, and we'll probably end there. I had more, but we can wrap that up maybe early next class. So here's an example. It's a very simple example, so that we can kind of appreciate that hey, chain rule works very mechanically, and easily so that we don't have to worry too much. But this, the connection to this with all of our course is that if you saw torch, right? I just showed torch as a package to get our tensor, the three-dimensional array. Torch does backpropagation behind the scenes for us. Okay, for all the loss functions or all the functions that we define, typically most functions will be defined. So you can actually, without explicitly saying, what's the gradient, actually doing the minus alpha times that, you can actually say, here's the power, take an input, compute, just tell me the gradient of whatever I computed with respect to its input, it will just give you that number. Okay. Why? Because behind the scenes, it has helper functions which will do that for you at some, which you don't need to concern too much yourself as a user of that package. Okay. So let's look at this example: A, B, and C. A and B are getting multiplied, and C is getting added to the result. Okay. So what computations are happening? A simple multiplication and a simple addition, and these are all scalars. So it's a little bit easy. It's a pretty easy example. So the circles represent the compute nodes. So the H that we saw, like a blue circle, that's this could be this circle, it could be this circle. Okay. Now let's say G is the final output, right? G. Let's call the intermediate computation of this multiplication H. Okay. So A times B, let's call it H. Okay, just as a, I'm just trying to use the previous notation here. Okay. Then G is just H plus B. So let's focus on G related node here. Okay. So G related node, all it's saying is its local gradients. Okay, its output with respect to how much does B change when H varies. H is one of the inputs. How much does B change when C varies? Second input, right? How much does G vary when H changes? Because G is just H plus C, if H changes by 5 units, then G will also change by 5 units. If H changes by 1 unit, G will also change by 1 unit. So gradient partial derivative of G with respect to H is 1. Okay, that's kind of easy to see, but I'm just giving you like an intuitive explanation. Similarly, how much does G vary? G change when C changes by 1 unit or 2 units, same units. That's why the rate of change is the same, 1. Okay.
Why the same change? Because both are different.
No, like say if I add C, if I increase C by 0.5 units, how much does G change? You don't even need to know the original value of G. If C changes by 0.5 units, then G will also change by 0.5 units. Right? I don't need to even know the original value, but sometimes you need to know at what value you're changing it. Okay. Anyway, the partial derivatives of G with respect to its input are 1 and 1. And since let's start with the base case, it's just for simplicity. Partial derivative of G with respect to itself is 1. Okay. So you can think of this as the incoming gradient. Local gradients are 1 and 1. So the gradients getting passed back are just one on each side. One on each, path. Okay. What are we trying to do here, by the way? We want to find for this function the gradient of the gradient of G, which is the partial derivative of G with respect to A, partial derivative of G with respect to B, partial derivative of G with respect to C. Those three numbers, we want to stack them together. That's the gradient of G with respect to its inputs. Okay. But we broke down that G function into multiple parts, right? 2 parts actually, like the multiplication and the addition. And so what we're doing is now step by step back propagating from, okay, this little function here, we know everything about it. How does its output change with respect to its inputs? It's very clear since it's an addition of 2 numbers. These are the partial derivatives. So whatever incoming derivative I have, partial derivative I have, I'm going to multiply it 1 times 1 and 1 times 1, and that's what I'm going to pass back. By doing this backward computation, eventually I'm going to get the partial derivative of G with respect to A, partial derivative of G with respect to B, and partial derivative of G with respect to C, and I'll stack them together. That's the gradient of G. Okay, at that kind of at A, B, and C. Okay, now let's look at the next step. For multiplication, H is A times B. So how much does H vary when A is incremented by 1? Okay, it's B units. If A is incremented by 2, there is 2B units. So sorry, so how much does H change? It's exactly the multiple B multiples, right? I mean, you can see that, right? If I increment A by, if I add A plus 10, then it's 10B, so this is multiples of B. So partial derivative of H with respect to A is B. I'm just giving you very simple intuition. This is actually not very complicated. What will happen is you will actually, for multiplication, it turns out that partial derivative of H with respect to one of its input is just the other input. Okay. So here you can see that the partial derivative depends on what the current value is. Okay, what the current value of the other input is. Okay, which is okay. I'm just interesting note. Okay, now we have the for multiplication node, we know what the local derivatives are, as in like its output, how much it varies with its input. Okay, we know that. Now there is an incoming gradient, okay, which is incoming, sorry, partial derivative, which is equal to 1. So 1 times b is what's passed back all the way, here. Similarly, 1 times a is passed back here, and here it's just 1. Okay, so based on that, the partial derivative of g with respect to a is b. Partial derivative of g with respect to b is a, because a times 1. Okay, and so the partial derivative of g with respect to c, we already computed it here. It's 1. Okay, so it's just multiplying gradients locally with incoming gradients to get the to pass on the combined thing to the the thing which precedes it, and then if you do that, you can get the gradient of the function with respect to whatever, wherever, whichever, whatever units, whatever parameters you want, inputs you want. Okay, let me not get into the second example. This is the second example, which exactly just has 3, not 3, but like 4 units, and I would highly encourage you to look at this example because this is simple example, it doesn't have too many complicated functions, but this is what's if you can get this, then you're kind of more confident in using the tool. Okay, it's not so much about understanding this so that you implement it behind the scenes. It's more about, hey, there's no black magic in Torch or TensorFlow or JAX or whatever, MXNet. I don't know. There are many such tools, but that's what they're doing behind the scenes. Okay, that's the capability which currently I guess NumPy doesn't have. That's why we need this extra thing. Okay, but yeah. So let's. I mean, that's the explanation for that, and we will skip this. Yeah, we'll skip these slides. We're just talking about the same gradient descent. Once you understand backpropagation, then you come back to gradient descent. That hey, we need the gradient. Let's use the gradient in the batch gradient setting. So what I want to show is I don't want to show the code now, and we'll do it in the next class. But I want to show the punchline because that's actually useful for motivating what we're going to do in the next class, which is that the classifier that we saw, we have been seeing that Wx plus b, the lead logic regression model. There's actually we in our code base or in our repository, we actually have those examples that you can try out. Okay, on Google Colab, you can actually import any GitHub repo or a notebook if it's in a GitHub repo directly, right? So you should try to open some of these functions. Like I think that's in this folder. Sorry for the bad naming acronyms there. There's a feed-forward network, which we'll study next lecture. But a linear classifier example is that snapshot in the slide deck. If you see that, I've imported it already in Colab, but you can try it out. And first few cells are not related to that. So the example starts from here, okay? And you'll see that that's a linear classifier that's trying to do a 3-class classification. That's logic regression model essentially. But what you want to take from this code is how you've defined the W, the B, the loss. At least there's a lot of backpropagation happening in this code. It's not using PyTorch or it's not using TensorFlow or anything. It's just showing what the local gradients are. Explicitly, it's computing it. But that's fine. For this code, for this data, clearly that linear classifier doesn't work, right? So what is the linear classifier that can separate the yellow dots from the blue dots or the blue dot from the red dots? There's none, right? And that motivates. We want to get around linear models by either doing feature engineering, which will solve the problem, or go to nonlinear models. Okay, you can do either. And here's the example. Here's the situation currently. Okay? We have to do something. This is the best linear classifier for this data. Okay, so linear classifier has logistic regression. If you remember, it's only going to give you linear decision boundaries. Okay, so it's just plotting the linear decision boundary. Okay? This part is blue, this part is red, this part is yellow, and you can see that yellows are its loss is not 0 clearly on the training data itself. So this is the best linear classifier. So to fix this, either you do feature engineering, you kind of create squares, products, logs, whatever you want to transform your inputs. It's only a 2-dimensional data set, or you pick a nonlinear model. Okay, And we're gonna pick a nonlinear model. I kept saying logic regression is an example of a neural network. We will see that next lecture. Okay. And that nonlinear model will be just a nice progression from logic regression, a feed-forward neural network, and that will fit much better to this data. Okay. So let's end there. If you have any questions, you can come forward. Otherwise, we are done for today.